All right, welcome back to our summer lecture series. Today I'm going to try to finish off kind of a little introduction to HartreeFock, and I guess how this might differ from any information you might have seen about HartreeFock before is that I'm actually going to try to derive the actual HartreeFock equations today. We'll see if I can fit that in. But hopefully we're in a good state to do this because we got all the notation out of the way last time, and I mentioned what HartreeFock was in a kind of a hand-wavy way last time. So now we're ready to get into the nitty-gritty. But before I do that, let me ask if anybody has any questions left over from last time about kind of what HartreeFock is or what its goals are. Okay, if not, what I've done is I've gone ahead and written up on the board some equations we had last time, just to kind of remind you what it is we're doing. So in HartreeFock, you optimize the orbitals, the molecular orbitals, to get the minimum energy by the variational principle. So you have to know what the energy is. That's the energy. It consists of one electron terms and two electron terms. The one electron terms give you the kinetic energy of the electrons and their attraction to the nuclei. The two electron terms give you the electron-electron interactions. The first bit is called the Coulomb term, and it gives you just basically what the Coulomb repulsion between electrons are, given that the fact that if an electron's in orbital, you don't quite know where it is at any given time, so you have to figure out the probability that it's at some place with chi star chi. And then given that probability, the electron 1's here and electron 2's there, their repulsion would be that. But then you don't know what orbitals they're in. Maybe you have them in orbitals I and J, maybe they're in orbitals K and L. So you sum over all the orbitals. That gives you the Coulomb repulsion. And then this piece we mentioned last time is the so-called exchange piece, which just comes out of the anti-symmetry principle, the fact that the wave function needs to change sign if I change sets of coordinates for any two electrons. That term falls out of that. So those are all the pieces, and then we're going to start to minimize this thing. So what we're going to do is we're going to set up we're going to use the method of undetermined multipliers and set up some Lagrangian with some unknown multipliers. And the point of this is that I really want to minimize this, but I want to minimize this while preserving the orthonormality of the orbitals. And if I didn't preserve the orthonormality orbitals, the math would get much, much harder. So it's good to preserve that, and I do it this way. So this is kind of a constraint that I put in. I want this term to go to 0. Ij is the overlap between orbitals I and j. It should be Kronecker delta Ij if these two are orthonormal. And so I throw that in, and I'm going to minimize this function L. And the way I'm going to do that is I'm going to use a method of variations. I'm going to see what is the variation in L, how does it change, if I change one of the orbitals chi I to chi I plus some change delta chi I. So, well, what would the change be? It would be some change in the Hartree-Fock piece plus a change in this piece. These undetermined multipliers are constant with respect to chi, so they're not going to move. And neither is this Kronecker delta, but I could vary this overlap by varying this. Certainly, if I change this, I will change the overlap. So that. This term, the change in the overlap is what? Well, if this is the overlap and I do this tweak, then I get a piece that stays the same, but I don't care about that. I care about the change in this. I've already subtracted that out. And the change in this would be, well, the change in chi I, the overlap of that with j, or chi I stays the same, and I have a little delta in chi j. Now, does anybody notice I've actually got one term missing? Does anybody notice what that is? Too early in the morning to catch. So the piece I'm missing, you could say, well, wait a minute. If I just sort of literally substituted this down into here, I get a chi I chi j. That's the part I already have. That's not a change, so I don't worry about that one. I get a delta chi I with chi j. I get a chi I with delta chi j, and I would get a delta chi I with a delta chi j. Okay, so I have this guy. And that would be a change. The reason I didn't write it down, and I'll cross it out again, is because the assumption is whatever change this is, it's small. So if I have a small change in chi I times a small change in chi j, this is on the order of small squared, and so I'm not going to worry about it. So I'm only worrying about first order changes. Okay. Right. Well, that's the easy part. The hard part is what's the change in the HartreeFock part, which is the part we really worry about. This other thing is just kind of a constraint to keep things over the normal. Well, all right. So how does this change if I do this substitution? Chi I goes to chi I plus delta chi I. Well, I have to more or less plug this in up here. So let me do that. See what notation I'm using. No, okay. So delta E HartreeFock is, first part's one electron piece. Well, I could have a delta in the first part. I'll go ahead and write chi's. Remember, I was just the shorthand for chi I, so I'll go ahead and exchange it back out to chi I here. So there could be a delta on the left. There could also be a delta on the right. H delta chi I. And again, there would also be a delta chi I, but that one is going to be very small, so I'm just not going to worry about that because I'm assuming these changes will be small. Plus, I guess I might have had hats on the H yesterday, whatever, it's the same thing. One electron operator. And then I plug in here. Now, this is going to get kind of annoying. I guess I'll write it down for pedagogical reasons anyway. But I'm going to get a bunch of terms. Because I could tweak this one, or that one, or that one, or that one. Or 2 at a time, 3 at a time, or 4 at a time. But I'm going to knock all of those out because they'll all be small. So this is going to be 4 terms, and that's going to be 4 terms. That's a little tedious, but I'll write it down anyway. We'll see if we can simplify it in a second. Okay, so the first bit is going to be, again, I just means chi I, so I'm going to spell out delta chi I. So delta on the first one. Chi j plus chi I delta chi I j plus, maybe the first 2 are the same, chi I, and maybe the third one changes, delta chi j, plus, if I can squeeze it on here, the fourth one changes, chi j, delta chi j. Okay, that's fine. Then I've got the exchange term, and I do something similar. And even though my notes kind of work it out this way, I think let me switch notations again, if it won't bother you too much, because I think it's just as easy to write. Maybe I'll go back to calling these just I and j, and I'll just call delta I and delta j. Why not do that? That's slightly easier right now. Let's try that. So let's see. So it's minus a half. So if you'll let me, I'm just going to call this delta I, j, I. That might be a little easier to read back there. Plus, we'll understand that we distribute this minus sign through everything. So that's if I tweak the first one. If I tweak the second one, it's I delta j, ji. And if I tweak the third one, it's ij delta j, I. And if I tweak the fourth one, it's ijj delta I. All right.
Is that a minus sign?
Yeah, this is a minus sign. And what I mean, I could put brackets here or something, but I mean that this minus sign distributes through. So those are all subtracted terms. All right, does that make sense so far?
Is there a physical interpretation you can give to the delta chi I being in the bra as opposed to the ket for those first two terms? Or are those two terms going to come out the exact same?
For the first two terms, like this?
No, on the left of that, just...
Here?
Yeah.
Well, it's in the bra here, but it's in the bra here, but it's in the ket here, so it can go anywhere. And you'll notice also that I'm in the bra here, but then I'm in the ket over here, so it goes everywhere. But there is a way to kind of simplify this. One thing I'll remind you of, last time we talked about that some of these integrals are symmetric. For example, the two electron integrals, which one's electron 1 and which one's electron 2 is irrelevant because they're just dummy indices, and I integrate over the coordinates of electron 1, I integrate over the coordinates of electron 2. So I could flip-flop which one's electron 1, electron 2. It wouldn't matter. It wouldn't change anything. What does that mean for these symbols? Well, it means that electron 1 is on the left by definition in one of these symbols, and electron 2 is on the right. So if I did a flip-flop of electron 1 and 2, I would swap the bra and the ket, the left and the right sides, and it would be the same thing. So maybe I can use that to simplify some things. Let's see. If I flip left and right, do I get a term that looks like something I already have, and can I combine them? Close, yeah. This guy looks a lot like this guy. Now there is another difference though. This is I's and that's J's. This is I's and that's J's. If I flip-flop them, then I'd have J's and I's, and that wouldn't quite match. But that's also okay because I'm summing over all possible I's and J's. So I and J is also a dummy index. So for this one, I could call the one on the left I and the one on the right J. But for this one, I could redefine I equals J, J equals I, and then this would become chi J, delta chi I, delta chi I, which is that. So this term here, do I have another color? This term equals that term because I can swap I and J because they're dummy indices, and I can swap left and right because one's electron 1 and one's electron 2, they're the same. So those turn out to actually be the same thing. Does that make sense? Okay. What else can I do? I should be able to do something similar for this and this, right? Because everything seems like it's coming in pairs. So can I? Yeah, I can do exactly the same thing. I can swap left and right to take the delta over to the left, and then I can again swap I and J, and then that term becomes exactly that term. So that is also a good thing. So that'll save me, what, half my writing. That's as simple as that. And I can do the same thing down below. Or can I? Let's see. Most likely. Here's the delta I, J, J, I. If I swap left and right, do I get anything similar to that? This one looks like that one, except again, I became J, J became I, but that's okay because I'm summing over all I's and J's, so I can redefine which one's I and which one's J in one of the sums, say that one. And then I can swap left and right, and that becomes delta I, J, J, I, which is that. So those two terms are the same. And then, obviously, this is going to have to wind up being the same as that. And it is, because if I swap left and right, I would get J delta I, I, J, which looks just like that if, again, I swap which one's I and which one's J. This kind of renaming dummy indices that you're summing over or integrating over is extremely common in quantum chemistry as a way to simplify what you're writing down. So we'll do that a lot. Okay, so in fact, maybe I'll go ahead and rewrite that in a sort of simplified way. Let's see, do I need to do anything before I do that? Let's go ahead and rewrite. Let's go ahead and rewrite all that. So I'm going to take this, plug it in for delta HF, and then I'm going to take this bit and plug that in here, and then I'm going to rewrite the whole thing. And since I don't have room to do that without erasing this, I'm going to go ahead and erase that. But I'm going to take my results and I'm going to plug them in for delta L. I'll do that here. And I'm going to use my simplification of combining the purple terms and the green terms. All right, so delta L is now what? Sum over I, delta chi I, h chi I, plus chi I, h delta chi I, plus sum over I and j. I'm going to use this slightly easier to write shorthand, I think. I'm just going to call that delta I, j, plus I delta I, j. Those are the two Coulomb pieces. Notice I had a half before, but I got rid of it. That's because I combined two terms and that 2 canceled in half. Subtract the exchange terms, sum over I and j, delta I j, j I, plus I delta j, j I. And maybe to make this clear, let me put some brackets here to show that the sums go across like that. Okay. I'm not done yet because I still had this piece. So let me write that down. Minus, minus ij, epsilon ij, these are my undetermined multipliers. Delta I j plus I delta j. Get rid of my chi's on that one too. Maybe I should do these to these consistent. Let's try that. Just call it everything. Chi's are too much to write. And this lets my subscripts be a little bigger, a little easier to read. But yeah, that's consistent and nice. Sort of nice. All right. That's how a tweak in an orbital, delta I or delta J, changes this Lagrangian setup. Now, I need to do some fiddling around with this to try to show you how this term relates to that term. So I need to play with that a little bit. All right, what I'm going to do is I'm going to take some complex conjugates. Let me take this piece. Let's play with that. Sum over ij, there's a minus sign in front, but let's not worry about that for right now. Epsilon ij, I delta j. And what is the symbol again to make sure nobody's getting lost? I delta j would mean, that may not fit, would mean integral chi I star of x1 times this delta chi j of x1 dx1. So it's just an overlap integral. It's this function overlaps so much with that function, and what is that overlap? It might be 0, it might be 1, it might be something, depending on how things are verbalized. All right, so this guy, let me play around with this. I'm going to take the complex conjugate twice. I can do that, right? Because if I take a complex conjugate and then take another one, I'll get back what I started from. So I'm going to do that. One of them, let me just write a big outer complex conjugate. So, and then an inner one, let me take the complex conjugate of each piece separately. Well, these are some numbers. They might be complex. So I'll just write epsilon ij star. That's how you take the complex conjugate of a number. This thing, how do I take the complex conjugate of that? Well, it's this integral. So to take the complex conjugate of the integral, I take the complex conjugate of each piece. So the complex conjugate of this would be complex conjugate of that, but I've already got a star on it, so complex conjugate twice gives you back the original function, so that becomes chi I, and then this delta chi j would get a star on it. All right? So that would give me, what would give me integral. The complex conjugate of that would give me the integral chi I, oops, double star, so now there's no star, delta chi j star. All right, now what is this back in this notation? Well, the thing that's complex conjugate is always on the left in the bra. The thing without a complex conjugate is always on the right in the ket. So that means I write bracket delta j I. Because I've reversed which one's which, because I took a complex conjugate. And in fact, in general, anytime you have an overlap integral and you take its complex conjugate, it's the same thing, but you just reverse the bra and the ket. That's the short way to do it, without having to go back through this to remind yourself. All right, so what? What can I actually do with that? Doesn't seem super useful at this stage. Let's see where I'm at. We're good so far. Now, I'm summing over all i's and j's. So which one's I and which one's j is relevant. So let me rename them. Ij now it becomes epsilon ji star, and now this becomes delta ij. That's the same thing. Okay, so I can do that. But now, suppose I have a matrix, epsilon, and I take the complex conjugate of that matrix. Well, if you have a whole matrix like this, and you take the complex conjugate of the matrix, normally we call that an adjoint. To take an adjoint of a matrix, you flip the matrix around, you transpose it, and then you take the complex conjugate of each piece. So, thinking in kind of matrix terms, epsilon ji star is a matrix element of the transpose, and it should equal, if I know that these guys belong to some kind of Hermitian matrix where the complex conjugate is the same, is the adjoint is the same as itself, that guy should just be epsilon ij. So this guy, I'm going to write it as epsilon ij because I'm going to assume that whatever these multipliers are, they belong to a matrix which is actually a Hermitian matrix. And for a Hermitian matrix, the adjoint of the matrix equals itself. Now, do I know that the epsilons are Hermitian? Yes, although I'm not sure I want to prove that to you now because that gets us too much into a tangent. So let me just say epsilon winds up being a Hermitian matrix, and because of that, I'm allowed to say, well, take that matrix, adjoint it, each element, epsilon ij becomes epsilon ji star, and if it is a Hermitian matrix, those two things have to be equal to each other. So we'll go ahead and use the hermitivity of epsilon, even though I don't have time to prove that. But it's basically because this entire Lagrangian is going to wind up being real. Okay, so that's that. And then this other guy, well, it's just what I had in the last stuff. I guess I can't do a whole lot with that. Star. Now, with some changing indices and arguing that epsilon should belong to a Hermitian matrix, what did I wind up with? Where did I start from? There. I started from this piece. That piece was where I started from. And then I said, I'm going to take this complex conjugate twice, which doesn't change it. And then I did some stuff, and then I wound up with this. But this is the same as this first term, except that I've got this outer complex conjugate. So what I've tried to just prove to you is that this term is the complex conjugate of that term. Once I permute I and j, then I can kind of decide that that must be true. So that's cool. That means I have two terms, but one's just a complex conjugate of the other. And it turns out all these other bits where I have two terms, like this and this, are all complex conjugates of each other. In fact, this, look at that for a second. How do I turn this into its complex conjugate? Well, I just reverse bra and ket, and then I also change the operator into its adjoint. But this is a one-electron operator, which is a piece of a Hamiltonian, and a Hamiltonian is a Hermitian operator, so this is a Hermitian operator. So H hat dagger equals H hat. So this doesn't change when I take the complex conjugate. And then the only other thing I do is I swap bra and ket. So if I swap bra and ket, I get that. So this guy is the complex conjugate of that guy. And so on and so forth for every term in here. Every term, like say this, is the complex conjugate of that. And this is the complex conjugate of that. So everything's a complex conjugate of something else, which is great because it means I can write down half as many terms and then say plus complex conjugate, which is what I'm about to do. Yes?
Can you explain how the second term is equal to the third?
The second term is equal to the third.
Yeah, on the last line.
These two?
No, on the last line.
This one and this one?
Yeah.
Okay. Yes. All I did to go from here to here is I swapped I and j. Am I allowed to swap I and j? Yes, because I'm summing over all I and j. So it's just a dummy summation. Other questions? Okay, so let me rewrite it now with this new realization that the reason I have doublings of terms is that things are just complex conjugates of each other. Is it obvious that this is a complex conjugate of this? Maybe not. Let me remind you what this means again. Remember, PQRS is a shorthand for this integral chi p star x1 chi q of x1 1 over r12 chi r of x2 chi s of x2 and this one's a star. So if I took the complex conjugate of this, I'd flip that and that, I'd flip that and that. So if I look at this term, if I flip this and this, I get that. And if I flip two j's, well, I just get two j's back. So this really is the complex conjugate of that, and that really is the complex conjugate of that. All right, let's see if we can summarize all that now. Now our terms are starting to get a little bit more well-behaved. There we go. So the variation in L, delta L, equals sum over I, delta I, H I, plus, I'm not going to write the complex conjugates right now, plus sum over ij, delta I, j, minus delta I, j, I, minus sum over ij, epsilon ij, delta I with j, plus the complex conjugate of that whole thing. And if I'm at the minimum, what does delta L need to equal? 0. Because I'm at the bottom of some well. And I'm down here, so if I make some little tweak in chi's, this is maybe delta chi or something. If I make some tweak in chi, the Lagrangian or the Hartree-Fock energy shouldn't change at first order. So if I'm at a minimum, that needs to be equal to 0. Of course, that would also be 0 if you're at a maximum. But it turns out the Hartree-Fock equations we're going to derive almost always give you a minimum, not a maximum, so you're usually okay. All right, so what? Now I guess what I'm going to do is write this all back out, reminding you what each of these pieces really is. So now the notation will get more complicated again for a second while we try to remember H and what's that and whatever. So let's do that. Yeah, all right. No help for it. It's a little bit messy. One electron term, what is that? It's an integral over some electron coordinate. Here we've got delta, I will switch back to chi's now, I guess. Chi I star x1. I'm going to put a big bracket here. One electron operator, x1 times chi I of x1 plus. So that's this. Hopefully that looks like that to you. Just switch back out of direct notation back into integral notation so that it hopefully is clear what's going on. Sum over j, chi I of x1 times integral dx2 1 over r12 chi j star of x2 chi j of x2. What is that? That's this guy. Let me get my color coding back. Let's do this one is that. Plus that. This piece is common to everything, so I pulled it out, but it's part of all the other pieces. Coulomb term is going to be that one. Now I need to do the exchange term. That's going to be subtracted minus chi j of x1 integral dx2 1 over r12 chi j star of x2 chi I of x2. That's supposed to be I. So that's the exchange term. Do I have another color? Brown. This is this piece. And then you might say, wait a minute. Exchange term has I, j, j, and I, but you only have j, j, and I. Right, but that's, again, because I pulled out this delta chi I all the way out, because it's part of every single term here. Or all of those terms, anyway. Now I'm done with my square bracket, I think. Right? No, I also pulled it out of, not done with my square bracket. I'm left with this epsilon piece. Let me fit that on. Can I squeeze it on into the board here? Minus sum over j, epsilon ij, chi j of x1. Now I'm done with my square bracket. Plus the complex conjugate equals 0. Wow, look at all that. So I'm doing some integrals, but they're all okay. 1 electron integral, kinetic energy and attraction of the nuclei. 2 electron integral for Coulomb repulsion. 2 electron integral for exchange. And this undetermined multiplier to kind of keep things over the normal. That all has to equal 0. Now, I'm going to make a key observation, which is this. This delta L needs to be 0 if I'm at a minimum. But this tweak in the order, suppose I'm adding it, okay? Then if I do some little tweak, the energy or the Lagrangian shouldn't change. This is obviously a multi-dimensional surface, because I have a whole bunch of chi-i's, I could vary chi1, chi2, chi3, or do any of them. And I could change them by any amount as long as it's small. So whatever delta chi-i I pick, any I, any amount, as long as it's not big, this thing still needs to equal 0 because I'm at the minimum. So it doesn't matter if I go, 0.001 units or 0.005 units, as long as it's kind of a small bit. It's irrelevant, and I can do it to any of them. So in that sense, this delta chi-i is arbitrary. You can kind of pick anything reasonable, and this equation still has to hold. So what does that mean? The equation doesn't really depend on delta chi-i. That's not the guts of the equation. It's arbitrary. So if this is true for any reasonable delta chi-i you pick, then it must be that the stuff in brackets is 0. Because put whatever you want here, as long as it's small, and it's always true. So if you put anything here and it's always 0, it's not that this is 0, that wouldn't make any sense. It's that this is 0. So the bracketed thing is 0. And certainly 0 plus its complex conjugate is still 0, so that's okay. You could say, maybe you could say, well, what if this thing is pure imaginary? And then a pure imaginary thing plus its complex conjugate, that would be 0. Yeah, that might work. That might work. But it's going to turn out that pure imaginary things won't work. I don't think I can prove that to you right now. So the thing in brackets has to be 0, though. All right, so, even that wouldn't work, I think, because the way I plucked out of asymmetry. All right, anyway. The thing in brackets is going to have to be 0. Okay, so what does that mean? Well, it means if I want, I can now kind of trash this part and just write the thing in brackets and say, well, all right, if that's 0, what does that entail? In fact, that's actually what I'm going to do. So, this thing in brackets, what does it mean if that's 0? Well, I'm going to take this bit here and I'm going to pull it over to the other side. So I'm going to say this stuff here, the 3 color-coded terms, equals this other thing. And certainly if that's true, then the sum of those equals 0. So that's going to give me just a slightly different way to write the equation. So h of x1 times chi-i of x1 plus sum j not equal to I integral dx2. I'm going to write this as absolute value squared, if you let me. What's absolute value squared? It just means the thing times its complex conjugate. So this is just a tiny bit quicker for me to write than chi j star chi j. It means the same thing. So chi j absolute value squared, 1 over R12. That acts on chi I of x1 minus, that's the Coulomb term, exchange term, j not equal to I, integral dx2 chi j star of x2 chi I of x2 1 over R12. All that applies to chi j of x1. And that stuff equals, because I'm pulling this over to the right-hand side now, sum over j epsilon ij kj chi j. Okay. Well, it's a really nasty equation. It's called an integral differential equation because I have integrals and I have derivatives, like this guy has a kinetic energy operator, which is a second derivative. So there's integrals, there's derivatives, there's the integral differential equation. This is really, really nasty. But I can manipulate it to make it a little more convenient. Let's talk about this piece. What is this? Well, this is the probability that electron 2 in orbital J is at some position x2. And if it were there, then some orbital, some electron 1 in orbital I might feel some potential generated by this. And what potential does it feel? Well, it feels 1 over R12, the distance between them. And again, I'm in atomic units, otherwise I'd have E squared over 4 pi epsilon naught. So this kind of generates a potential that electron 1 feels, and that gets me back at this Coulomb term. And this is just this exchange part, which is kind of hard to explain. And those are my random undetermined multipliers that I put in to kind of originally put a constraint on for orthonormality. All right. Well, this guy, because this is a potential that electron 1 feels generated by electron 2, and using the probabilities because I don't know where the electron is, so whatever, integrating over all space, I'm going to call this guy, this piece here, J hat. And I'm going to put a sub J because it does depend on what orbital is generating the potential. Different orbitals have different probabilities. So this is the Coulomb potential generated by an electron in orbital J, and it's felt by electron 1. I've integrated out over x2, so it's not a function of x2, but it is a function of x1 because I've got the 1 over R12 there. Well, it's equal to that. So this guy is that. This thing is a little harder to write, but I'm going to write it this way. Let's make an operator called kj, which is also going to be a function of x1. Kj I can't just define this way. I've got to define it based on what it acts on. So let's say it acts on an orbital I, chi I, x1. And when you act this operator on this orbital, you're going to get this stuff I have up top. Integral dx2 chi j star of x2, 1 over R12, chi I of x2, times chi j of x1. All right, that's going to be my definition of kj. Now, given that, I can rewrite this complicated integral differential equation in terms of these new operators just to make it kind of look a little bit more compact, which looks like a valuable thing given where we're headed here. So now I'm going to have operator H, 1 electron operator, plus sum over j not equal to I, j sub j, function of x1, minus sum over j not equal to I, k sub j, x1. That whole big mess of operators acting on orbital I, chi I of x1, equals sum over j, epsilon ij chi j, x1. In a more symbolic form, that's what my HartreeFock equations have turned into. Now, I can make 2 simplifications to this. First off, for reasons that I mentioned earlier about the 2 electron integrals, suppose I did have I equals j. It turns out for the case I equals j, you can go back here and look at this if you want and convince yourself. For the case I equals j, ji equals ki. They're the same if they have the same orbital. So because of that, or ji, maybe I should say, ji minus ki acting on some orbital chi will cancel and give you 0. You could go back and prove this from the definitions if you want. So if I want, I could go ahead and remove my restriction on the sum, because if I do have j equals I, it's going to go 0 anyway, so you can include it or not. It kind of doesn't matter. So I will include it just so I don't have to keep writing this j not equal I thing. And the other thing I'm going to do is to realize that over on this side, I have the freedom to choose a set of orbitals such that that Lagrangian undetermined multiplier matrix epsilon becomes diagonal. I could do basically what's called a change of basis procedure, where I take all the chi-i's that solve this equation and rotate them such that I can diagonalize this matrix. So I will do that so that I have a diagonal epsilon. So now let me do those two things at the same time. And now let me define an operator f. F, acting on x1, is h, not acting on x1, f of x1 is h of x1 plus sum over j, unrestricted sum, because the I equal j part doesn't matter anyway, j sub j of x1 minus k sub j of x1. So f is basically this thing above. And then this is going to turn into the diagonal matrix. So that means all the stuff I can write in shorthand as f of x1 times chi-i of x1 equals epsilon sub I. I could write I, but let's write I. Diagonal element of this matrix, once I've diagonalized it, chi-i of x1. If I write it that way, it looks pretty easy. And the only complication is that this f operator hides this complexity of all these other little bits. But, you know, whatever, it's a complicated operator. Some operator acting on this orbital gives me the orbital back times an energy. Well, times a multiplier. It's going to turn out to be an energy. That's the HartreeFock equation in its kind of most simple form. And it's an eigenvalue equation, right? This is the eigenfunction of this operator. Anytime you have operator times a function, giving the function back times a constant, it's an eigenvalue equation. So we can work with this. It's a little bit of a tricky eigenvalue equation, though, because the operator f is defined in terms of j's and k's. J's and k's are defined in terms of chi's. So you have a little bit of a catch-22 here. You need the chi's to make f, but you can't get the chi's until you can solve this equation based on f. So it's kind of circular. So that's why this is called the self-consistent field procedure. What you do is you go ahead and just guess some chi's, and then based on your guess chi's, you get a guess j and a guess k. It gives you a guess Fock matrix. Then you solve, well, Fock operator so far. You find the eigenvectors and eigenfunctions of this operator. That gives you a new set of chi's. Then you plug those chi's back in to j and k, form a new Fock operator, and then you solve this until you get to self-consistency. And normally this basically works. Now, how do I actually go about solving this equation? Because it's obviously complicated. Well, here's what we do. This was the contribution of Rotan. Rotan said, let's use a basis set, a set of predefined functions. This gives us a so-called HartreeFock Rotan procedure. What I'm going to do is I'm going to say chi-i, my orbital, my molecular orbital, is going to be a combination of some functions, mu equals 1 to k, some number of functions, c mu I, chi mu, And I'll put tilde to denote that these are the pre-selected basis functions. All right, what do I mean by basis functions? You just make up some functions, and you say, these are the functions I'm going to use. And then you solve the HartreeFock equations using those functions. Now, clearly, if you pick some good functions, then you'll get good molecular orbitals, and if you pick some crummy functions, you'll get terrible molecular orbitals. In general, the more functions, the better, because this procedure will minimize the energy by taking the appropriate linear combinations that the molecule wants. So if you give it some good stuff to work with, it'll tweak it and find the right combinations and do the best it can. And the more functions you give it, the better, and the more of those functions look like what the orbitals really want to do, the better. People have worked hard at defining pre-selected basis sets, and they're available in the literature and in the common programs. And those are the things we call 631G star, CCPVDZ, TZV, PP, things like that. We have all these acronyms for these standard basis sets. That's the topic of a talk Lori's going to give. I'm just going to say they exist. If you're a physicist, you'll actually use plane waves as your basis. Chemists tend to use Gaussian functions centered on atoms. And in the old days, they actually used what are called Slater functions, but those have fallen out of favor because Gaussians are much more convenient to work with mathematically and computationally. All right, so I'm going to insert that. Let me do that into my Hartree-Fock equations, into that. So I'm going to take this and just plug it in here, basically. So let's do that. So the Fock operator acts on some sum. I'll call this one nu. C nu I chi nu tilde equals epsilon sub I, sum on the right, call that nu, but it's a different sum. C nu I chi nu tilde x1. That's what happens when I substitute this expansion into the Fock equation. Now what I'm going to do is I'm going to multiply on the left. On the left multiply by one of these basis functions, chi mu star of x1, and integrate. So let's do that. I'm going to have the sum over nu is going to pull out. Integral dx1 chi mu tilde star of x1. That's a basis function. Fock operator in the middle. We got a chi nu tilde on the right. Equals epsilon sum over nu, c nu I, integral dx1 chi nu tilde star, mu, chi mu tilde star, x1 times chi nu tilde x1. Now, I want my molecular orbitals to be orthonormal, but in general, my basis functions will not be orthonormal unless I somehow make them be, but I don't normally do that. So this integral here on the right is not 0 because the basis functions, the tilde functions, are in general not orthogonal functions or orthonormal. So this integral is some number. So I can't simplify by making that Kronecker delta or something like that. All right, that's fine. We can work with that. Let me define some shorthand. This guy, it's a classic formula for a matrix element. I've got an operator, I've got some function on the right, I've got some function star on the left. I integrate over it. That's a matrix element. I'm going to call that, I'll switch to capital F for now, if it's okay with you. F mu nu. F mu nu is that. So it's called matrix element. You could make a matrix of these, obviously, because they depend on two indices, and so I could for all possible mu and nu, I could evaluate this, put it in a big two-dimensional matrix. This guy, likewise, I'm going to define that as a matrix. I'm going to call that S mu nu. Okay, so that's good. So in matrix form, what does this equation look like? Well, it's sort of there, I guess, already. I'm going to rewrite it in the interest of clarity. It's a sum over nu, F mu nu, C nu I equals epsilon sub I, sum over nu, S mu nu, C nu I. Now, if any of you have worked much with matrices, you can immediately see this equation's fine. It's true for all I. But I could also write this in all mu, I guess. But I could also write this in kind of a matrix form. This is the same thing as matrix F times matrix C, but double under bars to denote a matrix, equals matrix S times matrix C times epsilon, where epsilon is a diagonal matrix with these eigenvalues going down the diagonal. It's a diagonal matrix. That's not bad, because this now has turned into from a complicated integral differential equation to a matrix problem. Matrix problems are easy to solve on computers. Well, in general. This one may be hard if you're doing a big molecule, but still. This is something we like. So how do I solve this? I need to evaluate, using my basis functions, how the basis functions are acted on by F. F in turn is made up of H, J, and K. I can work out what H, J, and K do to a basis function. And so if I know that, I can get these integrals somehow. If I have these, I can fill out a matrix of these. And, well, that's what I need. So the known quantity is F, and then the unknowns are C and epsilon. S is also known because if I know the basis functions, I can work out these integrals. So you're given F and S, and then you solve for C and epsilon. And this is an eigenvalue equation, but it's a little bit of a tweaked one. If I didn't have S, it would be a normal eigenvalue equation. And there are standard procedures. You can give a computer a big matrix F and say, give me the eigenvectors and eigenvalues, and you can do that. And it's only if it becomes giant that you have to do some special tricks. This is called a generalized or pseudo eigenvalue problem because this metric matrix, this overlap matrix is here. But there are techniques for dealing with that as well. So this is kind of a known thing if you can only supply F, and we can because we can figure out how F acts on these basis functions. The only trick being, because F depends on chi's, you do have to do it self-consistently. You guess chi's, you get an F, you do this, you get C's. From the C's, that gives you, what do the C's give you? Gives you what the molecular orbitals are in terms of the guess functions, the basis functions. And then you form a new F, and you just do this until it doesn't change anymore. So what do you get out of it? You get the molecular orbitals through, if you know C, you know chi-I, you get the molecular orbitals. The chemists use basis functions that are Gaussian centered on atoms, and so they're kind of atomic orbital-like quantities. So we can loosely call these atomic orbitals. That's why sometimes you see this acronym, LCAO-MO theory. This stands for linear combination of atomic orbitals, molecular orbital theory. It just means your molecular orbitals are a linear combination of atomic orbitals. That's what we just did. So this is LCAO-MO theory, or HartreeFock roton theory. Obviously, the person who figures out how to evaluate how H, J, and K act on these arbitrary basis functions has to do some complicated math, but this has all been solved years ago, and the equations exist, and then you just have to write a computer program to do it. What else do you get out of this? You get these epsilons. So epsilon is this diagonal matrix where you have epsilon 1, epsilon 2, up to epsilon n for the number of electrons. those have the interpretation of orbital energies. It's the energy that an orbital has, or an energy an electron has in a given orbital. What does that mean? Approximately, or loosely speaking, it means how much energy would it take to rip an electron out of that orbital. And this is reasonably accurate for, if you use a decent basis set from HartreeFock, for the highest occupied molecular orbital. So the minus of the energy of the highest occupied molecular orbital is approximately the first ionization potential of the molecule. This is called Koopman's theorem. Koopman's theorem says that you get the highest occupied molecular orbital energy, it's a negative number, so then you multiply it by -1 to get a positive number, and that is approximately the ionization potential of the molecule. This is also sort of roughly true for other electrons, like the HOMA -1, the HOMA -2 if you go down, but it becomes more and more of an approximation. The best numbers usually come from the HOMA. But if you want a rough idea, then the other orbital energies are fine too. What goes wrong when you try to do this on a computer? Well, sometimes this procedure, since it's iterative, can get stuck. And Renee saw this on some calculation, I think, or Chris saw it. One of you guys saw this last week, I think, where the calculation just gets stuck, and sometimes it'll alternate between two solutions. It'll hop between one solution and the other solution, and it kind of never goes anywhere. That occasionally happens. It also sometimes happens that you land on what's called a false HartreeFock solution. So you actually minimize, you get delta L to equal 0, but you can sometimes be at a local maximum instead of a local minimum. So suppose you're here, if you tweak delta chi, either way, energy doesn't change, but you're actually at the maximum. That doesn't happen very often, but it occasionally happens. How can you tell if this happened to you? Normally you don't, unless you just get strange properties, like your dipole moment seems backwards, or something just seems wrong, and then you think, what's going on? The only way to really detect this is to compute what's the curvature. So what's the change in the HartreeFock energy, the second derivative of the HartreeFock energy with respect to changes in orbitals. You can compute that, and then you'd see that, oops, the curvature is the wrong way, I'm at a maximum. That's called a HartreeFock stability analysis. And there are programs that exist that will take the second derivative of the energy with respect to orbital rotations, and you want all positive eigenvalues, that means you're at a minimum. If you get a negative eigenvalue, it means you're at a maximum in some orbital rotation parameter, and then you realize, oops, I accidentally landed on this bad solution, and you can fix it. That maybe happens, I don't know, 2% of the time or something, unless you're working with a really nasty molecule. So it doesn't happen very often, but it happens enough that it can cause people trouble. You can obviously get a bad calculation if you use too small of a basis set. So Lori will talk about basis sets. You can also sort of get a bad calculation if you use too big of a basis set. Now, how can that be? I already said that the bigger the basis set, the better. And that's true in a variational sense. The bigger the basis set, the lower the energy will be. We know the lower the energy is, the closer the wave function is to the right answer through the variational theorem. So how could it ever be a bad idea to use a big basis set? Well, that's because HartreeFock itself, even the idea of HartreeFock, going way back to a single Slater determinant, is an approximation. Nobody ever promised that the wave function really could be written as a single Slater determinant. The single Slater determinant is an approximation. You're saying, well, this is what I'm going to try, let's see how it works. So it turns out you make an error by doing that, and what does the error come from? Well, mathematically it comes from you restricted your wave function to a single Slater determinant. Okay, so that's easy for me to say. What does that mean physically? It's not obvious, but physically what it means is you've implicitly assumed that each electron only sees the average charge field of the other electrons. And you can maybe see this if you go back to when I was writing J's and K's. You see that orbital chi I sees this kind of integrated over stuff from orbitals j. When you do that integral and have orbital I see this average field from orbital j, that's not what's really happening in the system. The electrons see each other instantly and not some averaged over thing. And that leads to what's called electron correlation. The electrons see each other, they try to avoid each other, and that's not captured by HartreeFock. So electron correlation effects are an error in HartreeFock, and it turns out sometimes you get a favorable error cancellation if you use a basis set that's not the world's largest basis set. If you use the world's largest basis set, there's no basis set error, and then you have no basis set error to cancel your HartreeFock error. So sometimes you luck out, and you actually get decent HartreeFock results if you use a modest basis set, because the basis set introduces an error, which, if you're really lucky, has a sign which is opposite from the sign of the HartreeFock error, because it misses electron correlation, and those can kind of cancel, and you get decent results. So frequently, people don't use a basis set bigger than polarized double zeta type basis sets, because that's kind of where there's a good error cancellation. In quantum chemistry, these error cancellations are sometimes called Pauling points, and a Pauling point just means you made a couple choices like HartreeFock and double zeta that go together well because they both have errors, but they tend to cancel. Most of quantum chemistry relies on error cancellations of one kind or another. We never really can do a good enough job, because to really get the basis set right would have an insanely large number of basis functions that we just can't do practically. To really get the wave function right would involve an insanely long expansion of many, many Slater determinants that we can't really do. So it's really a game of finding good combinations of methods and basis sets where you get decent error cancellations, and you can get better and better results by going up the chain of Pauling points. So the next Pauling point, the next Pauling point. You could do MP2 with a different basis set or a couple cluster with a different basis set. You can get better answers, but you always have to balance your basis set choice with your treatment of electron correlation. Okay, that's all I can squeeze in. I kept you a little bit longer than an hour, so sorry for that. But that is hopefully a nice mathematical overview of what really is going on in HartreeFock theory, and then maybe at the end a little bit of insight in terms of things that can go wrong and what actually happens. For those of you who may be interested, especially students working with me, I will post some notes. In fact, they're already posted. I guess maybe I'll put a link to them or something. I have some notes about guiding you through how to write your own HartreeFock code. It turns out it's surprisingly easy, given how complicated the mathematics is. The hard part is getting the integrals, but I'll supply those in some file. So given the integrals, sort of forming these matrices and diagonalizing them and getting the eigenvectors and eigenvalues, this is something that's very doable. I actually had a summer student who got excited about this and wrote the program in less than a day. So it's not infinitely hard to do. And when you write one of these, it gives you a lot of insight into what the program's really doing under the hood, and then that helps you understand when things go wrong, how they might have gone wrong, things like that. Any questions before we wrap up? Okay. Well, thanks for coming.